Hello, everyone. My name is Ramya, and I'm here to present our poster towards automated phenotype definition extraction using large language models. Firstly, I'd like to thank the organizers for giving us a chance to send a recorded version of our presentation so that we can share our research with you all. So, with the explosion of digital health data, the potential to use the information for improved patient care and innovative medical research has grown exponentially. So, traditionally, phenotyping relied on manual methods involving comprehensive literature reviews and collaborative efforts among clinicians and researchers to define specific health outcomes, diseases, or conditions. This process, although thorough, is time consuming and not easily scalable. So, the development of large language models revolutionized electronic phenotyping. These models, equipped with hundreds of billions of parameters, leverage few shot learning to achieve high performance with minimum training samples. This capability significantly reduces the time and effort required to define and refine phenotypes, making the process more scalable and adaptable to the fast paced advancements in medical research and emerging health crises. But there are a few problems with LLMs in medicine, though they have revolutionized research. They are not reliable, they usually hallucinate, they are misleading, and they could lead to harm. So, it is very important to evaluate the results given by LLMs before we actually start using them. So, what did we actually do here? Our work is anchored in two main objectives. First, we defined a standard evaluation task specifically tailored for this domain. And second, we evaluated various prompting approaches for extracting phenotype definitions from large language models. Evaluation is key here to make sure that LLMs are producing useful and reliable outputs. So, to create an evaluation set, we used 10 professionally created phenotypes, 5 from PKB and 5 from Odyssey Phenotype Library. So, extracting phenotypes from sources like Odyssey is easier due to their structured format and use of the OMOP common data model. In contrast, PKB offers flexibility without a mandated model, requiring more effort to adapt algorithms across different systems. So, to streamline this, what we did was we manually curated and developed automated code to extract and format elements from PKB phenotypes for automatic evaluation. So, to evaluate prompting approaches to extract phenotype definitions from LLMs, we experimented with several methods like zero shot learning, one shot learning, iterative prompting, and seeding, and finalized a prompt for consistent results. You can see the prompt on the screen here. So, we evaluated LLM efficiency in two scenarios. First, we compared definitions from GPT 3.5 and GPT 4 and comparing GPT 4 definitions with human curated ones. We have defined three different metrics, which are code overlap, which means we want to see how many codes or concepts agree. Then we have string overlap, where we want to see how many strings or concept names are overlapping. And finally we have logical matching, where we want to see if there is an agreement between inclusion and exclusion, or both of them between 3.5 and GPT-4. We also wanted to look at human definitions versus GPT-4. And finally, we also did a little bit of research on, or little bit of analysis on, inconsistencies and incorrect definitions. So the first part of our result was to see how well do GPT versions do against each other. So here, GPT models sometimes generate precise codes but struggle with textual strings, showing variability in outputs across iterations. Interestingly, LLMs effectively extract logical conditions for including or excluding codes in phenotype definitions. This variability in code and string overlap is partly due to the diverse code systems used in literature and the definitions. What about humans versus GPT-4? GPT-4 generates codes with marginally higher reliability than textual strings or concept names. Despite generating fewer codes overall, GPT-4's codes may have a higher positive predictive value for accurately identifying intended phenotypes, suggesting their specificity and relevance are high. This implies that GPT-4 might be averaging codes from sources and surfacing the most popular ones. What about GPT hallucinations with codes? Here we found that hallucinations were present in both the models, with with GPT 3.5 exhibiting a higher tendency for inaccuracies than GPT 4. The results highlight the model's weakness, particularly their inaccuracies and hallucinations. These issues were more pronounced for less documented phenotypes, highlighting the need for cautious use and meticulous verification of LLM generated data. Enhancing training methodologies to address literature scarcity on specific phenotypes is crucial to improving model accuracy. So what can we conclude here? While GPT 3.5 and GPT 4 show promise in generating medically relevant codes, it is still a challenge to achieve consistent textual output and avoid inaccuracies. Despite hallucinations and inconsistencies, GPT models can serve as a valuable initial steps or augmentation tools, significantly streamlining and improving electronic phenotyping methodologies. Thank you for giving us this opportunity. Please feel free to reach out to us if you have any further questions. Thank you.